Hi guys, today's Leetcode daily problem is count of interesting subarrays. So we are given zero index integer array whose name is nums and an integer modulo and an integer k. In this nums, any element that satisfies nums of I mod modulo equal to k, then it is a special element. Now if we see all the possible subarrays of this nums, if any subarray every subarray will contain some special element. Suppose it has count number of special element, and if that count mod modulo equal to k, then that subarray will be known as interesting subarray. So we have to now tell what are the total possible number of interesting subarrays present in this nums array. Now, like we'll see example so that we can better understand this question. Now, here this is the given nums array modulo equal to 3 and k equal to 0. Now, if we talk about a special element, then if we see 3 mod 3 is 0, which is equal to k, so this is a special element. 9 mod 3 is equal to 0, equal to k, this is also a special element. And 6 mod 3 equal to 0, equal to k, this is a special element. And 1 mod 3 is 1, which is not equal to 0, not equal to k, so this is not a special element. So if we consider subarray containing element 3196, so here three special elements are present, and if we do 3 mod 3, which is equal to 0, so this is a interesting subarray. And if we take another subarray containing only one as element, then here also the count of special elements is 0, and 0 mod 3 is equal to 0, equal to k. So this is also a special, like interesting subarray. So here two interesting subarrays are possible. We'll return 2 as our answer. Now we'll see brute force approach. So it is very simple. We'll find all the possible subarrays, then we'll calculate count of special element for all the subarrays, and then we'll return total number of subarrays that satisfy this condition. That is the number of subarrays that has count mod modulo equal to k. But here finding all the subarrays will only involve big O of n square time complexity, then calculating count of a special element and seeing whether this condition satisfies or not. It will involve another big O of n. So overall time complexity is big O of n cube. So this is not feasible solution. Now we'll see some concept before seeing the final approach. Like if it is given that a minus b mod modulo equal to k, it means that when we divide a minus b by modulo, we get k as remainder. So we can simply write a minus b equal to q into modulo plus k. On rearranging this, we can write b equal to a minus k minus q into modulo, taking mod on both sides. So we can write b mod modulo equal to a minus k minus q into modulo mod modulo. Now this q into modulo is always a multiple of modulo. So this we can like ignore it. So we can write v mod modulo equal to a minus k mod modulo. Now to be in the safe zone, like sometimes this can be negative. So to ensure that this value always remains positive, we'll add one more modulo here. Like it will not impact answer. Suppose we are calculating 5 modulo 7, it is equal to 5. If we calculate 5 plus 7, that is 12 modulo 7, it will also remain 5. So just we are adding one modulo here to ensure that this value always remains positive. Now we'll see final approach. So we'll maintain prefix count array that tells us number of special elements we have explored till that index. By using this prefix count, for any subarray with indices L to R, we can find the count of special element. Like we'll find the count of special element from 0 to R minus count of special element from 0 to L minus 1. This will give count of special element from L to R. Now we'll simply for iterate for R, and for each R we'll calculate how many L are possible that forms interesting subarray. That is the subarray which satisfies this condition. We have already seen this we can write as this, like prefix count of R minus K plus modulo mod modulo equal to prefix count of L minus 1 mod modulo. So now this simply we can say that how many times this prefix count of L minus one mod modulo has appeared in prefix sum before, that many L will be possible. That many like subarray will be possible for if we keep this R as fixed. So we'll maintain a map that contains frequency of this prefix count of L minus 1 mod modulo, so that we can directly use that and we don't have to calculate again and again. And finally we'll add that frequency to our answer, and at last we'll return answer. Now we'll see code so that we can better understand our approach. We have taken initially prefix equal to 0. This prefix will act as prefix count of R. We haven't taken prefix array because prefix count of L we can directly find by using this formula. So there is no need of array. Initially we have taken answer equal to 0. We have taken an ordered map where we'll maintain the frequency of prefix count of all the elements. And we have taken frequency of 0 equal to 1 because consider subarray that is interesting from index 0 to R. That means it doesn't need any other element and any other count. So it will search for whether frequency of 0 is present or not. So we should give frequency of 0 equal to 1 so that we consider it as valid interesting subarray. Now we'll traverse from 0 to last index of nums. That means we'll traverse for all the elements of nums, and if any element satisfies this condition, mod modulo equal to k, that means it is a special element. So we'll increment our prefix count by 1, and we'll add our answer, the count of prefix of L minus 1. After that we'll update our frequency map by prefix mod modulo key by incrementing it by 1. After this loop is done, our answer will contain the count of all the interesting subarrays. So we'll return our answer. Now, if we talk about time complexity, then only we are traversing for all the elements of nums. If there are n elements, then our time complexity is big of n. If we talk about space complexity, then in this map we are storing all the elements from 0 to modulo. So modulo minus 1. So space complexity is big of modulo.